Hello and welcome to Multiloop Circuits in PHYS 1204. In this unit we're going to be learning no new physics, we're just going to take physics we already know and apply it to slightly more complicated circuits than we've looked at in previous units. We're going to start with circuits that contain only resistors and batteries. I'm just going to start by going back over a couple of things from quite a while ago and updating them a bit. So we've seen that two circuit elements, no matter what they are in series if one end of one is connected to one end of the other and there are no junctions in between. So these elements A and B are in series, but these ones are not because there's a junction between them. And we've seen that however much charge enters one of them must go on to the other, or to update that in terms of terminology, we now know whatever current flows through one must also flow through the other. Similarly, we've seen that two circuit elements are in parallel if both ends of them are connected together with only junctions, no other elements in between. And so these elements, A and B, are in parallel, but these ones are not because C is in between them at one end. And we've seen that the potential difference across two elements in parallel has to be the same, and we understood that at the time in terms of path independence of potential difference. But we could also understand it in terms of simply writing the loop law around each of these. Here's a familiar circuit which you saw in an activity earlier in the term, where these resistors were all identical light bulbs. And let's start by thinking about this switch being closed, in which case we know that whatever current goes through the first resistor splits to go through the other two. The other two resistors are in parallel, and so we know the potential differences across them are the same, and Ohm's law tells us that if the potential differences are the same, then the currents through them must also be the same. But now let's think about what happens when we open the switch. It's fairly obvious to most people that since the current that went through the first resistor was shared before by the two resistors and now it all goes through the one resistor, then that light bulb must get brighter. But many people will predict that the brightness of this bulb stays the same. But in fact it gets dimmer, and people often have a hard time explaining why. So how do we explain why this one gets dimmer when we open the switch? Well, notice that Ohm's law applies to both. And in one case, I1 and I2 are equal. In the other case, I1 is equal to I2 plus I3. And we know I2 and I3 are equal, so that in fact tells you that I1 is twice of either I2 or I3. Well, that implies that the potential difference across this first resistor is greater than the potential difference across this second resistor in this case, whereas over here those potential differences are equal. But what's true in both cases is the loop law. If we think about this loop in both cases, the loop law is the same for both. And what that is telling us is that the potential difference across these two resistors has to always add up to the EMF of the battery. And so since they have to add up to the EMF of the battery, but in this case we know that delta V1 is bigger, we know that it's greater than half the EMF of the battery. You can actually show it's 2/3. Whereas in this case it's exactly half of the EMF of the battery. Well, so the potential difference across resistor 1 decreases when we open the switch. And again, Ohm's law implies that the current decreases. This bulb gets dimmer when we open the switch. The real point of showing you this, though, was to illustrate a very important general principle. We changed something in one part of the circuit. In particular, we removed this resistor. And as a result, the currents through every other circuit element changed. This is generally true, that when you change anything anywhere in a circuit, the currents through and potential differences across every circuit element elsewhere in the circuit will change. There are exceptions, of course, and I'll leave you to think of what the exceptions are, but in general you can bet that when you make a change to somewhere in the circuit, everything else will have changed as a result. This general principle that changing something anywhere in a circuit changes what happens elsewhere is useful when thinking about voltmeters and ammeters. So an instrument that we measure potential difference with is called a voltmeter. And let's think of what we need to do to measure the potential difference across a circuit element. Well, we want the potential difference across the voltmeter to be the same as the potential difference that we're measuring, and so we connect them in parallel. But now if there was a current through that element before, that will in general change because now some current goes through the voltmeter. Well, that's no good, because if we've changed the current through that element, we may have also changed the potential difference across it. So we deal with this by making sure that voltmeters always have a very large resistance so that the current through them is small and it has very little effect on the current through the thing that we're trying to measure the potential difference across. So for a typical benchtop voltmeter, 20 mega ohms is a pretty typical resistance. On the other hand, an ammeter is rather different. An ammeter is what we use for measuring current, and so if you think about how we need to measure current, we need to make sure that the same current will go through the ammeter as there is current going through the thing that we're measuring the current through, and so we have to put the ammeter in series with the object that we're trying to measure the current through. That will always involve breaking the circuit to insert the meter. But now think of what that will do. In general, you would expect that since the ammeter must have some resistance, that will have slightly reduced the current. And so again, that wouldn't be very useful. We deal with that by ensuring that an ammeter has a very small resistance, and so it has a negligible effect on the current through. Fairly typically, ammeters have resistances in the range of milliohms. An important consequence of that very small resistance of an ammeter is that you must never connect an ammeter in parallel with something else, because if you do, you will have put the same potential difference across it as the other thing, but it has a very small resistance, and so a gigantic current will run through your ammeter. In general, that would destroy your ammeter, except that most ammeters have a fuse in them that will burn out to protect the ammeter. But now you have to replace the fuse. There are some pieces of terminology that will be more important to us now that we're looking at circuits with multiple loops. So first of all, a point where more than two wires join is called a junction. And so in this example circuit, there are 4 junctions. Any path that joins a pair of junctions without passing through any other junctions is called a branch. And so in this example circuit, we have 1, 2, 3, 4, 5, 6 branches. The particularly important thing about branches is that if you know the current anywhere in a branch, since there are no junctions along the branch, the current has to be the same everywhere else in that branch. So in this example, we can see that the current through the battery has to be the same as the current through resistor 1. And so the fact that we have 6 branches in this circuit tells us that there must be 6 different currents. Finally, a path from any point, which returns to the same point, is called a loop. So for example, in this circuit, here's a loop, and here's a loop, and here's a loop, and those are the most obvious ones, but there are more loops. This is a loop, and this is a loop, and this is a loop, and finally the loop around the outside. So there are in fact 7 loops. Here's a general strategy for solving for all the currents in a circuit using Kirchhoff's laws. First, start by setting which way you think all the currents are. It doesn't actually matter if you get them all right. All you're doing is setting sign conventions for the equations that you're going to write. Next, note how many independent currents there are. In this example, we've already seen that there are 6. That means we're going to need 6 equations to be able to solve for them all. Well, look, we have a junction law for every junction and a loop law for every loop. So in principle here, we can write 11 equations for this circuit. But they won't all be useful. Many of those equations will just be sums of other pairs of equations. A good rule of thumb is that for every hole in the circuit, or in fact what we call a mesh, there will be one useful loop law. This doesn't imply that you have to write the loop laws for these loops. It's just that because there are 3 meshes, these loops around holes in the circuit, there are only 3 useful loop laws. So we can pick any number of groups of 3 of these 7 loops to write the equations for. Now, since we need 6 equations, we'll have to write 3 more equations, which will be junction laws, and then we will be able to solve. So I'm going to work an example, and I'm going to do this circuit, which might look a little more complicated than the other example circuit I've been using. In fact, this one turns out to be a little easier to solve. So I'm going to do exactly what I suggested, and I'm going to first set current directions. So it's fairly clear that this current is almost certainly this way. So I'm going to call that I1 because it's the current through R1. And it's also probably pretty clear that this one is this way, and so I'll call that I3 since it's through R3. And I know that the current through this battery, which I might call IA, has to be the same as I1, because they're on the same branch. Now, what about the current through this resistor? It's probably less clear which way that current is, but because of the way this battery is pointed, you might be inclined to guess that it's this way. It doesn't matter, it'll all come out in the wash once we solve. So the next thing I'm going to do is note that there are 2 meshes, right? Here's one mesh, here's another. And so there will only be 2 useful loop laws to write. But I'm not obliged to write a loop law for this simple mesh and this simple mesh. I could write any loops I want. So in fact, I'm going to write this loop, which I'll call loop A, and I will write the big loop all the way around like this, and I'll call that one B. Now I have 3 currents to solve for, and that gives me only 2 equations, so I'll also have to do a junction, so I'll do this junction, which I'll just label alpha, so I have a name for it. Now it's time to write our loop laws, and I'm going to write the law for loop B first. I start here, I go up through the battery, which is a potential rise because I'm going from the negative terminal to the positive. Then I go through resistor 1 with the current, and so I see a potential drop. And then I go through resistor 3 also with the current, and so I see another potential drop, and there is that loop law. Well, I'm both mean and lazy, so I'm not going to write the loop law for loop A. You are. So pick which of these is the correct one.